Okay, so far we've looked at some general how to use an exponential function and some word problems, and now it's about their graphs. So that's what 6.2 is all about. So first, let's just look at a very basic exponential function. You could kind of think of it as kind of one of the type of parent functions, kind of the very most basic function. So we're going to graph f of x equals 2 to the x power. So you know it's an exponential function if that x up there is your power. Okay, now for an exponential function, we don't have to be as um, careful as to what we plug in. When we get to graphing logarithmic functions in the next few sections coming up, we are going to have to be a little more careful. Here, we're just going to plug in -1, 0, and +1. That's pretty common, okay? Especially for our exponential functions, where if you'll notice this x here, there's no changes we've made to the x. It just says x, okay? Now, let's think about what 2 to the -1 power is. Well, 2 to the -1 power, the only job of a negative exponent is to flip whatever it's touching. It takes the reciprocal of whatever it's touching. So that's the same as 1/2. And then we're going to plug in 0, and then 2 to the 0 power is always 1. So remember, everything to the 0 power is 1. So that's two main things to remember about exponentials is if you have a power that's negative, the job of the negative is to take the reciprocal. If you have 0, the job of that is to make it 1. And then 2 to the first is just 2. Okay, so let's put that on the graph, but we have some other pieces and parts we have to worry about. Let's just put those on our graph. So at -1, we are at 1/2. At 0, we are at 1. And at 1, we are at 2. So let's just put those on there. And then there's one other little piece of information that we have to know. This type of graph has a horizontal asymptote. So the horizontal asymptote for this graph, if there is not a number hanging out here, it is always 0. So let's put that on there. Now this graph, some horizontal asymptotes, you can kind of touch it and then come back around, but you're going to follow it. This only follows it on one end. So now let's graph what the picture looks like. So what it does is it gets super close, super close, super close, and then there is this exponential growth. So that's what the graph looks like. So now we have this graph. So now let's answer some of the other questions that we have about this graph. The domain for these are all real numbers. We can plug in any x value we want. Nothing messes it up. You can plug into an exponential, whatever you want. You can plug in positives, negatives, fractions, decimals, whatever. The range, though, because of that horizontal asymptote, the horizontal asymptote is either going to indicate where the graph is heading, that minimal value, if the graph is above it, or sometimes they can be flipped upside down. But for this case, if you think about 0 is almost the lowest value. No, we're never going to hit 0. We're going to get super close to 0. So we indicate that with a parenthesis on our 0. And then if you think about the y values, it's getting to almost 0, and then it's going up as high as it wants. So for the range of an exponential function, usually one end will either be going to positive or negative infinity. The other end will either head to that asymptote. Okay, so that's very common. So let's talk about end behavior. So let's do the left end. As the x is heading to the left, negative infinity, the y value, as long as it hasn't been flipped upside down, will be heading toward the horizontal asymptote. So it's heading to a y value of 0. That's our horizontal asymptote. So one end is always heading to the horizontal asymptote. And if you've discovered the one end that's going to the horizontal asymptote, the other end is always going to either positive or negative infinity, because it's going to swoop way up or swoop way down if it's flipped upside down. So here, as x goes to the right, that's positive infinity. Our y value is going up to positive infinity. So this is referring to the fact we are heading to 0. That's our horizontal asymptote. This is the fact that we are going up, 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 way, way high. Okay, so our end behavior for an exponential function, one is always going to the asymptote, one end is going to either positive or negative infinity. It just depends, you know, depends upon the function. If you put a negative in front, that will flip it so it will look like that. But that's kind of the main idea. So this one is indicating we are heading to a height of 0. This one, if we go to the right, is saying we are heading to a height of positive infinity. Okay. And then the last thing here, I think, oh, there's a few other things. Okay. So let's talk about the intercepts. Now, these graphs will sometimes hit the x-axis, but only if we have something that would have pushed it down. So it depends on where the horizontal asymptote is. This particular graph has no x-intercepts. 2 to the x will never equal 0, so that's why that happens, and that's where that horizontal asymptote is. But the y-intercept we already found, we plugged in 0, we got a value of 1. So the y-intercept is the 0.01. Remember, y-intercept, no matter what we've been doing so far, to find it, you just plug in 1, get a number, there you go. These functions will either be always increasing or always decreasing along their domain. So this function, it doesn't appear, but it is getting a little higher, little higher, little higher, and it keeps going. So it is an increasing function. So it is increasing along the domain value from negative infinity to positive infinity. Okay. And we already said that our horizontal asymptote is y equals 0. So these have horizontal asymptotes. When we get to the point we are graphing logarithmic functions, they have the opposite. They have a vertical asymptote. So is that a little better? Can you see that? Okay. So that's kind of what your parent function looks like. Now, if you make that 2 like a fraction, it will decrease instead of increase. If you make that x a negative x, it will do the same. So there are some ways that we will be transforming these functions. So let's look at some things here. So these are the characteristics of the parent function, f of x equals b to the x. Let me zoom in there as much as I can. And I don't believe there's anything for you to write. Is that correct? Yes. So let's just follow along with me for a moment. If our b is a number bigger than 1, you're going to see that exponential growth. If our b is a fraction between 0 and 1, so any, it can be like 0.7, it can be 2/3, then it will go downhill. You're always going to have a horizontal asymptote. We consider it a one-to-one function, so the inverses we're going to find are the logarithmic functions we're going to do in the next few sections. And the main thing to remember, this is an exponential growth, and this is a decay. So why don't you just add a little note down here for me? Just make yourself a note that this is a growth, and this is a decay. and that the horizontal asymptote is 0. Did they say that? Yeah, okay. So you have kind of what the main characteristics are, but I want you to remember that this is going uphill from left to right. That one's increasing. That's why it's a growth, and this one is decreasing. That's why it is a decay. So in our lifetimes, we've seen things that have acted like this. They weren't completely exponential growths and decay, but when we first were seeing that pandemic hit and you saw those charts on the news, they were acting more in exponential growth, those number of cases. And then once about a year had passed and then vaccines came out, you started to see the opposite. You started to see that exponential decay. So exponential growth and decay happens in lots of real life applications, which is kind of interesting. So here we have one where, unlike the first graph we drew, where we had that base that was bigger than 1, now I want to show you one that has a base that is between 0 and 1. Okay, so let's take a look at what happens when we have a base like that. So we're going to do the same thing here. Since we have just that plain old x, let's just plug in -1, 0, and 1. Let's just plug in -1, 0, and 1. If you were to put into a calculator 0.25 to a power of -1, it's going to take the reciprocal of that. 0.25 is 1/4, so when we take its reciprocal, we get 4. 0.25 to the 0 power is 1. Anything to the 0 power is 1. And then 0.25 to the first power is just 0.25. So I think we're ready to graph it. Now I'm going to make that 1. So I'm going to count every 2 spaces, just so then we get a slightly better depiction here. If you ever change your scale, I'm going to keep the bottom ones though. If you ever change your scale, just let me know so that I can figure out how your graph paper is lined up. Okay. So the first thing we want to do is let's draw our horizontal asymptote at y equals 0. We've had no transformation of this function, so the horizontal asymptote is going to occur at 0. So let's put that on there. Okay, so now that that's on there, we've got some points. Let's go ahead and plug those points in, or I'll put those points on the graph. At -1, we are up at 4. At 0, we're at 1. And at 1, we're at 0.25. So those are our points. And our graph looks something like that. No, when you plug in a negative exponent, it flips it, but it does not change its sign. So 0.25, if you put into the calculator to the -1 power, its only job is flipping it, and then as soon as it flips it, the negative's kind of gone. No, it's plain old 4. Yeah, -1, x is the 0.4. Okay. So now that we have all that, we have everything we need then to answer all those questions. So it says domain. Remember, the domain of these is going to be all real numbers from -infinity to +infinity. The range is going to be affected by the horizontal asymptote. Our lowest y value is almost 0, so we put a parenthesis, but we can get as high as we want. And then we already have the horizontal asymptote on there, okay? So if your base is a number higher than 1, it's going to be going uphill from left to right. This is going downhill from left to right. That is why it is a decay. The other one was an example of a growth. So that will always happen. Now, if you change both the base and the x to be a negative x, it kind of reverses the process, which is kind of interesting. So if we start affecting the x, some things could happen. Now let's go ahead and we're going to talk about some of those transformations that can happen. Now, what hopefully you've got kind of a sense of, if it was a square root function, if it was a polynomial, anytime we manipulate the function in a certain way, if we add something on the inside, it moves left. If we add something on the outside, it moves up. Those things still work for an exponential function. But you got to remember, that's the function. That's the inside of the function. So if something happens up here, it's going to affect our x value. If something happens out here, it's going to affect our y value. So that's kind of the main difference when you're doing functions like this. Okay, so let's just talk about some of the things that can happen. If you add on the outside, it's going to go up. So add on the outside, it's going to go up. So an example of that is right here. See how they've taken our original exponential function 2 to the x? They've added a 3 on the outside and it's moved up. Always move the horizontal asymptote. So you see how our horizontal asymptote went up 3. Okay. If you subtract on the outside, it's going to move it down. So that's what we see here. They took our original that was in blue that we drew, that was our first graph that we did. And if you subtract on the outside, it is going to move that horizontal asymptote 3 down, and it's going to move all the other points with it. So you'll notice this point went 1, 2, 3 down. You know, every point would move 3 down. So the main rule that we learned from the very start when we started talking about transformations, if you add on the outside, it's going to move it up like this one. If you subtract on the outside, it's going to move it down like this one. So you have to acknowledge that if there's something added or subtracted, it moves the horizontal asymptote to that same location. It moves the whole function up and down. So this one moved up 3, this one moved down 3. So move that horizontal asymptote with it. That will make things go a little smoother, okay? So we know that. That's something we've done before. If we want to move it left and right, if we add on the inside, it's going to go left. What is that? Well, that's this one in red. Do you see how we've had a +3 to our function and it scooched it over to the left 3 units? If we subtract on the inside, it moves it to the right. And that's exactly what we've seen right here in orange here. We've seen that subtractant of 3 on the inside of the function. Inside of the function means by the x. It always means by the x. It has taken our original function and moved it to the right 3. So here I added 3 by the x, it moved it left. Here I subtracted 3 from the x by the x, and it moved it right. So add on the inside goes left, subtract on the inside moves right. That's very important that all of those same transformations, rules don't go anywhere. Next semester when we do trigonometry, same rules are going to apply. They give them a few different titles, they give them a few new terminology, but it's going to be the same exact thing. Okay. Stretches and compressions. If we put a number out here, what it does is it lifts it 3 times higher. If it happens to be a fraction on the outside, it compresses it downward. So see that original one, see how it went downward. Okay. If you put a negative on the outside, what happens? It's going to flip it over the x-axis. If you put a negative on the inside, it flips it over the y-axis. So negative on the outside flips it over the x-axis. Negative on the inside by the x, that's what I mean by the inside. We're going to flip it over the y-axis. So that's very, very important that we know that. Negative on the outside, see how that negative was put by the outside of the negative 2x? It flips it over the x-axis, doesn't change the horizontal asymptote. Flip it over the y-axis, we'll do that by touching the x. I don't know if you could see it real good, but there's a negative x right there. So exactly the same rules we have learned in the past. Negative on the outside, flip over the x-axis. Negative by the x on the inside, flips it over the y-axis. So that's super important. So hopefully when we start to look at these functions, you'll start to predict what's going to happen. Oh, there's a negative on the outside. Oh, it's going to flip over. Oh, I added 2 on the inside. Oh, it's going to move it to the left. So, you know, all those rules that we learned, you should predict what's going to happen, hopefully. So, just a kind of a summary. What the A is going to do, it might compress it, stretch it, or possibly flip it. And when I say flip it, I'm saying over the x-axis. The C is going to shift it horizontally, left and right. So if you have a number there. The D is a vertical shift up or down. So anything right there. Y equals D is always the horizontal asymptote. Okay. Y equals D is always the horizontal asymptote. So that's why those first functions, we didn't have a number sitting out there. So that's why it's 0. Until we move that up or down, this number here affects our horizontal asymptote. Okay. So that's super important. So now we have some that have some transformations. So let's go ahead and transform those things. Here's my suggestion. Remember how before I plugged in -1, 0, and +1? To the side, just take, where does x plus 1 equal -1? Well, to solve for x, you would subtract 1 from both sides. So now it's at -2. Now that should make sense because when we add on the inside, it shifts it to the left. So -1 shifted over to -2. Where does x plus 1 equal 0? That's at -1. That kind of tells me it shifted to the left. And where does x plus 1 equal 1? That would be at 0. So all of our original 3 points, normally I plug in -1, 0, and 1, have now shifted to the left, -2, -1, and 0. So I usually do that first. If I have a power that's different than x, I want to know where is that power going to equal -1, 0, and 1 so that I can get nice values when I plug those in. So that's the first step. Now that you do that, we're just going to plug them in. We're just going to do the math, okay? So if I plug in -2, I get -1 in my exponent. 2 to the -1 is 1/2, but there's a -3 on the back. So then I have to do, what is 1/2 minus 3? Well, 1/2 minus 3 is -2.5. Okay. Now I got to plug in -1. I'm going to get 2 to the 0, which we know is 1. But I have a -3 on the back, so that's going to take it down to -2. If I plug in 0, I get 2 to the first, which I know is 2. So then 2 minus 3 is -1. So I'm just plugging into the function. You can use a calculator for that, or you can, there's lots of ways to do it. So let's go ahead and set up our graph paper. Our horizontal asymptote this time has been moved down to -3. That was that D value up in the original kind of general form. That is what moves it down. So let's put a horizontal asymptote down at -3. And I'll just keep my graph paper the way it is. Okay, so now I have point. Yes. Can you say that one more time? This one? So you have to add 1 to that. So it's going to become a 2. And then 2 minus 3 is -1. Yeah, so don't forget. So do the power first. And then if there's a number on the outside, do that. So I did the power first. So 0 plus 1 is 1. 2 to the first is 2. Minus 3 is -1. Does that make sense? So I just kind of did the powers first and then minus 3 from them. And you can even do it. Sometimes it's helpful if you just list them right underneath the original function. That might have helped it be a little more organized. Okay, so now we got the points. So at -2, we're going to go down to -2.5. -1, we're at -2. 0, we're at -1. So let's put our graph on. And then if you did plug in 1, you get 2 squared, which is 4. 4 minus 3 is 1. I'm just going to give you a little extra point right there. So now we got our graph. Now we can do our domain and range. I kind of always have to do my asymptote before I do the graph because, So our domain is all real numbers. That's what it's been every single time. Our range is determined by where we put our horizontal asymptote. We have a horizontal asymptote at -3. So my graph is just above that, and it keeps going to infinity. So now I think that we have everything we need for that particular graph.
Can you explain one more time,
Yeah, so my original, anytime we have a transformation of our x, so if the x has changed, the normal good x's are -1, 0, and 1. So the best way to find what the new points will be to make things work nice, set that exponent equal to -1, solve for x, then set it equal to 0, and then set it equal to 1. And we have done that with other transformations. If our power has changed, or if our inside of our function has changed, set it equal, that inside equal to -1, 0, and 1 to find where the new good 3 points will be located. And you can see they all went to the left of what they originally were. Does that make sense how I did that? Okay. And that works for almost any function, whether we had any kind of transformation. Set the inside equal to -1, 0, and 1 is a good rule of thumb. Okay. Any other questions about that graph? Okay, let's do another one. Slightly different kind of transformation. What's great about this one is the fact that our x is just an x. You see that? That's just an x. So that means that plugging in -1, 0, and 1 is still a good strategy. Our horizontal asymptote, we have nothing sticking out that we have added or subtracted. This has not been shifted up or down. So that tells us that our horizontal asymptote is y equals 0. So let's go ahead and set up our graph paper. And let's go ahead and put our horizontal asymptote on. Okay, so we have some nice points to plug in. So let's plug them in. Okay, so remember, what are we plugging in? That's going to be -4 times 1/2 to the -1. Now, what does 1/2 to the -1 do? Its job is to flip whatever it's touching, take the reciprocal. So what's the reciprocal of 1/2? 2, right? It's just going to make it 2. So that's going to be negative 4 times 2. Remember, you always do that exponent first, get a number, then multiply by the outer number. So that's negative 8. Now let's plug in 0. Negative 4 times 1/2 to the 0. Anything to the 0 power, including a fraction, is always 1. So negative 4 times 1 is negative 4. And then if we plug in 1, we get 1/2 to the first, which is 1/2. So that's just negative 4 times a half. Half of negative 4 is negative 2. So now we got some really nice points. So at negative 1, I don't know if I can do this, but I'm going to see if I can pick up just that. Well, that'll at least help us. I forgot that this flipped over. So I'm like, oh, that's not going to fit. Okay, anyway. So let's plug in our points. So at negative 1, we are down at negative 8. At 0, we are at negative 4. At 1, we are at negative 2. So our graph looks like that. Okay. Now let's talk about why it turned out this way. If it was just the function f of x equals 1/2 x, so if the negative 4 wasn't there, it would look something like this. Okay, it's an exponential decay. But the negative 4 flipped it upside down, crossed the x-axis, and then the 4 kind of stretched it out a little bit. That's why it's kind of a little bit steeper than normal. But now we can answer the questions about domain and range. The domain, guess what? Oh my goodness, all real numbers. That doesn't seem to change. And it won't for these particular types of functions. The range. This one's kind of a weird one. What's the lowest we can go? Negative infinity. What's the highest we can go? Almost 0. So the negative on the outside of the function flips our range. So instead of going from 0 to infinity, it's going from negative infinity to 0. So it's always the y values from the bottom to the top. Yes?
Unless we have to like answer a question, like asking what a negative here or there would do.
Uh-huh.
Can we just do the problem normally?
Well, that's what I was doing right here. Yes. I mean, you always want to plug in some points. Negative 1, 0, and 1 is going to be good unless we've shifted it left and right. And then you might have to adjust your x's. Otherwise, just, you got to plug in some points. You at least want 3 of them so you can kind of find that curve. But yeah, you could just plug in points like normal. Mm-hmm. Are we good now with that? Okay. So you got your homework. Now it says to graph the function and its reflection about the y-axis on the same axes. Okay. And give the y-intercept, include the horizontal asymptote. So what you want to do for number 8, if I want to flip something over the y-axis, I put, well, you know what? I don't care about that part. Don't do that part. I don't need its reflection about the y-axis. So all I want you to do is graph the original, give me a little table, tell me the domain, the range, the y-intercept, and the horizontal asymptote. Same thing down at the bottom. Give me the horizontal asymptote, the domain, and the range. And they have just transformed that 2 to the x for that one. And then just more graphs. So it's just graphs and graphs and graphs. So you have a nice chunk of time right now to start working on these. Let me just kind of point you in the right direction. For the first 3, you can plug in negative 1, 0, and 1 for those without any issue. You can for 26 and 27. You can for 28 or 29, 30, and 31. The only one you have to adjust your x values, see how we have that -2? So those are the only ones. That graph has moved to the right 2 places. So I would not plug in -1, 0, and 1 for that one. So for that one, you would want to ask yourself, where will I get a number of -1, 0, and 1? And that's what you have to plug in for that one. All the other ones, plugging in -1, 0, and 1 will get you what you want. I need to see the horizontal asymptote for all of these. The only one that's a little funky is 28. You need to see where are your x minus 2, where are the x minus 2's going to equal the 3 good points you want. That'll transform that for you, okay? But other than that, they should be pretty straightforward. And you have just finished the 6162 notes. So please, if you could, turn those in right now. And then also Alex for 6-1 and 6-2, I believe is due tomorrow by midnight before the next one opens up. So please, if you haven't worked on your Alex, make sure you work on it tonight. So there you go. There is 6-2.